Welcome back, ladies and gentlemen. In this video, we're looking at this idea of conservation of mechanical energy. Now, that word conservation, when something is conserved, what's basically going on is it doesn't change. The total amount doesn't change. So it stays the same, unchanged, that kind of stuff. Well, mechanical energy. Mechanical energy is capital E, and we know what mechanical energy is made up of. If you were to take the kinetic energy of an object and you add to it the potential energy, especially gravitational potential energy, then you're going to get the mechanical energy. And so we got to look at both of them combined to talk about the mechanical energy. And the idea with conservation, since it's the same, some process happens, something happens, but the quantity of mechanical energy remains the same. And if it remains the same, then there is zero change, right? So that's true, okay? And this is going to be always a final value minus an initial value. All right, and if I add the initial value to both sides, it moves over here. So the final total mechanical energy is equal to the initial total mechanical energy. And this right here is the beginning of the equation for conservation of energy. What we're going to do, though, is, of course, we got to break it up and make it useful. Well, the mechanical energy is kinetic plus gravitational potential. So in this case, for the final values, we would have a final value of kinetic energy, and we add to it a final value of the gravitational potential energy. Oh, F there for final, right? So those two combined equal the final value of the total mechanical energy. On the other side, we have the initial. So we have an initial value of kinetic energy. We add to it an initial value of gravitational potential energy. Those two combined equal the initial mechanical energy. Now this is super important and super helpful, and I'm not going to write them down here, but you should absolutely be thinking, hey, I remember kinetic energy is 1/2 mv squared, and I remember gravitational potential energy is mgh. Now the formula over here is the same for those two. It's 1/2 mv squared, and those two is mgh. Now this is not to say, though, that the kinetic energy after something happens is the same as the kinetic energy before. No, what's going on is it means that actually changes. But whatever the change happens between these two has to be balanced by the change happening between these two. And you're going to see that. That means the total remains the same. And so here's what I mean. Let's imagine we have an object, and we're going to drop this object from some height. And so if it starts off just kind of sitting there, well, it's got no kinetic energy. Yeah, and then once we release it, it's going to start to lose that potential energy, and it's going to gain kinetic. And so here's the situation. We drop that thing out of that box. That box has a trap door in it. But before we open that trap door in the bottom, we can see that it's got a bunch of gravitational potential energy and no kinetic energy. But some very short time later, it's been allowed to fall some small distance. And so you can see after falling a small distance, the potential energy is less. And the kinetic energy has increased, not by much. But this is real important. The amount of loss of the potential energy, what was here, is now kinetic energy here. That means the total has remained the same. It's unchanged. If it falls a little further, you can see we've got even less potential energy and even more kinetic energy. And it falls even further. This is about halfway down. So we've lost half the potential energy. And that means, where did it go? Well, it went into kinetic energy. And that makes sense because as it falls, it's going faster and faster. So there's more energy of motion. It'll fall even further, even less potential energy. In fact, it's getting close to zero because it's close to the bottom. But the trade-off is it's gained a bunch of kinetic energy here. And then finally, once it hits the bottom, it has no potential energy left, and it's all kinetic energy. And I added these previous graphs for comparison, so check this out. Remember all the potential energy that it had here. Well, now it's all gone, and it's been converted into kinetic energy. So the total remains the same. Whenever you add these two together, the potential and the kinetic, there, or add those together, or add those together, you'll get the same answer, no matter what. Now, this is making a couple assumptions. This is like an ideal situation where there's no air resistance, there's no friction, nothing interfering with the object falling like this. But this is a really useful tool for us. And I just need you to understand, without diving into doing any calculations right now, it's basically a trade. We're trading one kind of energy for another. So, does it always look like that? Well, no, it won't always be something falling, and I want you to understand that as well. Check this example out. We've got this ball at the top of this ramp, and if we look at the vertical side, well, it's a 2-meter distance, and we look at the angled side here, the ramp side, it's a 4-meter distance. The ball happens to have a mass of 1.02 kilograms. All right, what I'm going to want to work out here is how much energy it's got. Well, the ball's sitting there, so there's actually no kinetic energy, and that's easy to recognize, right? So we can say, oh, K in front of that, kinetic energy is 0 joules. What about the potential energy? Gravitational potential energy is mgh, right? And so we've got the mass, g is 9.8, and height. Well, okay, so the height is now 2 meters. All right. And doing that math, it turns out we get an answer just, after rounding, we get 20 joules. Kind of a nice round number. Pretty convenient. Well, what that means is, what is the total mechanical energy, capital E? Well, we just add the two numbers together. We add the kinetic and the potential energies together. So the total mechanical energy is 20 joules at this location. All right, that's all of this applies to that location. And so if the ball were to roll off of this position and fall, or if it were to roll off and roll down the ramp this way, well, it's going to lose that potential energy as it falls, as it rolls this way, or as it falls vertically this way, right? But no matter what happens to it, no matter which way it goes, since energy is conserved, the total mechanical energy will remain unchanged. Yeah? Now, what if it, let's say it falls and it ends up going this way, ends up down there? Well, what's going on? So we know the mechanical energy remains unchanged, so the energy is still 20 joules. All right. Well, how much potential energy does it have here? 0. So gravitational potential energy is now 0. And we can figure out how much kinetic it has. So we take the total mechanical energy. It equals the kinetic energy plus the gravitational potential energy. And the gravitational potential energy was 0. And that was 20. And so we have a kinetic energy here of 20 joules. All right. So how much kinetic energy will it have if, instead of falling this way, if it rolls down to the left and ends up down here? Goes down that way. All right, what's going to happen? Well, let's see. Down here at the bottom, it's also, since energy is conserved, the energy down here is going to be 20 joules because it can't change. It's the same amount. Energy is conserved. Well, down here, the potential energy is 0, and what we have is the same situation. Mechanical energy is the kinetic energy plus the gravitational potential energy, but that's 0, so the kinetic energy is equal to the 20 joules there, J. Okay, so notice this is interesting. It doesn't matter which way it fell off, it's got the same kinetic energy at the bottom. It doesn't matter which path it took. That's interesting. Also, what this tells you, since the kinetic energy is the same, and it's the same object in either location with the same mass, well, then the velocities would be the same. We're not going to bother calculating the velocity right now, but the velocity here would equal the velocity there. Those are the same. It's going to go just as fast here as it does here, which might sound weird, but it's true. What you also should probably be able to figure out, well, it gets to which position first. All right, this is just a straight fall, and this is a rolling down the ramp. It's probably going to get to this one first. In fact, it will. And all that means is, well, it ends up at the same velocity here and here. But it takes more distance to get to that velocity there, and therefore the rate of acceleration is smaller here than it is here. This would be 9.8. This would be something less than 9.8 right there. That is conservation of energy. It's going to be a very useful equation, something we'll find. We're going to use this tool quite a bit. Thanks for watching. I'll catch you next time.